So on to the main event. So I have the pleasure of introducing Jasmin. Um, Winter skiing is a popular sport in Switzerland, but not all winter days and skiing regions are used to capacity. So Jasmin's going to take us through how to use Oracle machine learning features to work out where to go, and the prediction model will actually work out where you need to go depending on your capabilities, whether you're I'm mumbling my words here because I was trying to ad lib. Uncle Charlie, I'm surprised you didn't wind me up. Anyway.
Well, Jasmin's going to tell all about how to use Oracle machine learning to predict how many people you should staff and how many people are going to be in the parking lot and cool things like that.
Yeah.
So it's going to. I've seen this before, guys. You're in for a good one. And
so the best place to go. So Jasmin's a consultant at Scholzdell and lectures on software engineering, University of Applied Sciences, Northwestern Switzerland. What a lovely place to live. Her focus as a database developer lies on continuous integration and delivery pipelines, automation of recurring tasks, PLSQL development, data engineering, and data warehousing. Basically, she's a boffin when it comes to Oracle. So without further ado, let me hand over to Jasmin. You can take the floor, ma'am.
Thank you.
I need to stop my sharing. There you go.
Yeah, thanks. So also a warm welcome from my side. I'm the first speaker today, and I'm happy to talk about skiing. So as Charlie said, my presentation focuses on learnings of a data mining project that I have done last year. It will show an introduction into making predictions with the Oracle data mining functionality. If you have questions, just ask them in the Q&A panel. We'll try to answer them during the presentation or at the end of it. So now, a short thing about me that wasn't said. My name is Jasmin. I work mostly in data engineering. This means I do testing, I build continuous integration pipelines, I program in PL/SQL, and I work a lot with data warehouses. So why do I talk about data mining today? Because it's not one of my main activities. As I said, we had a research project last year as part of my master's degree in computer science, where we had to do data mining together with an industry partner. And this industry partner was a skiing area. And since this is about skiing, you get a second picture of me while skiing. I used to be a skiing instructor in Switzerland, so the topic was very exciting for me as well. Since I'm really a skiing fanatic. Now, as I said before, I'm currently doing my master's degree part-time, and one of the things you do during a master's degree in Switzerland is working together with industry partners. And our group of 3 was lucky to get a skiing area as an industry partner. And for me, as a skiing fanatic, that was just perfect. Now, what task needed our partner need to solve? A large skiing area is not only lifts and slopes. There are also restaurants. They have staff for operating the lift, staff for the restaurants, staff in search and rescue, as well as administration and back office. But they usually are an enterprise that is profit-oriented. And like other service-oriented enterprises, they have busy days as well as slow days when there are not many people skiing. And this depends on the day of the season, on the weather, on the snow, and many other parameters. This means some of the staffing must be operating on all days of the season, but others, like the restaurants, need less staff when there are less skiers. So the staffing varies with the amount of tourists that are visiting the area. So our research group got the task to predict how many skiers are in the skiing area on any given day in the season. The reason they want to know this is they want to be able to plan the amount of staff that they need on the mountain ahead. So the amount of staff on the mountain correlates with the amount of skier expected to ski on a mountain. And having a proper amount of staff on the mountain also means saving a lot of costs. If they have too much staff on the mountain and only few skiers, that means that they have high expenses. And this prediction is called a time series forecasting. So the goal of time series forecasting is to make accurate predictions about the future. So we needed to do some accurate predictions in this project. Now let's have a short look what skiing is. Wikipedia says skiing is the action of traveling over snow on skis, especially as a sport or recreation. And in a skiing resort that our industry partner runs, skiing is especially downhills. And this then looks like this on a good day. But why do skier numbers vary? This is mainly because we have different types of skiers that have different interests and different time schedules. There are mainly 4 types of skiers that we have. The first one is the local skier. He lives around a skiing area and goes skiing in every 3 minutes of his time. Then we have the weekend skier. He only goes skiing on weekends and only if the weather is nice. He doesn't like having too much wind, fog, or cloudy skies. The third skier type is the holiday skier. It's mostly families that will stay in the skiing region for a week during the school holidays. They buy skiing passes for the whole week because it's the only time they have for skiing. So they ski every day for this week to get the most out of it. And the fourth one is the single day opportunist. He's flexible in his time schedule and goes skiing for single days when the weather is nice. So those 4 types of skiers lead to a number of skiers on the mountain that is depending a lot on 2 factors: the weather, holidays, weekends. Okay, 3 factors. So the challenge at hand was to predict the amount of skiers to have an optimal staffing on the mountain. Now, if you want to start with creating a prediction model, the first thing you need is data, a lot of data. And let's have a look where we got that data from. A first set of data was provided by the skiing area itself. They provided historic skier data for the last 10 years, so we knew how many skiers were skiing on a certain day in the past. They also gave us information about their visitors, the countries of origins, for example, the duration of their stay, and some other informations. From fcal.ch, we took information about holidays of the different visitor countries. On the portal of Meteo Swiss, we got data about the weather of the past 10 years, like the wind speed, snow, rain, barometric pressure, humidity, and all the weather information you can possibly think of. On the Swiss Open Data portal, we got historic data about the national economy over the last 10 years. And when we had all this data, we realized it was a lot, not in volume. We only had a couple of 100 megabytes, but in variety. Only the weather data consisted of more than 100 features in the data set itself. We will discuss the challenges with a lot of data when we come to the creation of the data set later. Now, what tools did we use to make our analysis, or what did we decide to use? As a university project, we had the given requirement that only 3 tools can be used for the research itself. So we decided to use Oracle Autonomous Cloud as our data store and machine learning platform. We only used the tools of the always free database and not Oracle Analytics Cloud, because Oracle Analytics Cloud is obviously not a free tool. The second thing was that we needed to decide how we are doing our data analysis. We need to know if our data is skewed, how it is distributed, and for this we used Tableau. We probably could also have used an Excel spreadsheet for this. This was mainly about plotting some graphs and looking at the data and its distribution. And for all the data engineering part, we used SQL Developer. Now we have decided upon the tools we are using, but What else is necessary if I want to start predicting how many skiers are in my skiing area next week? Mainly, you need 3 things for building a successful prediction model. As we have seen before, first we need all the data that we can get. And we have seen where we got that from. And this should be historical data of the factors that influence your prediction. In our case, it would have been useless to have flight information, for example, because people rarely go skiing by plane. But it would be useful to have the dates of the local holidays, for example, because people tend to go skiing more often on weekends and on public holidays for obvious reasons. They have time. The second thing is know what you want to predict. Just having a bunch of data doesn't automatically provide you with wisdom. That's why it's important to have a well-formed question you want to answer with your data. It's a lot easier to work on a well-defined target and also know when this target is reached. It's also good to know when to stop optimizing your model. For this, you need certain criteria that have to be met, like the prediction must be accurate in 80% of the cases, for example. The third thing is you should have some basic statistical knowledge, not a lot, but some basic understanding of statistics will be necessary to interpret your data and make statements about the accuracy and the precision of your predictions. The rest you can probably compensate with very good Googling skills, or how it was in my case, I luckily knew the right people that can help me figure things out. And those people then tell you how to go forward or what to experiment. So when it was crucial, I had some help with my models. Now, if we want to predict something, where do we start? We start with asking the right questions that we really want to have an answer to. Because if you don't have a question, it would be a waste of time to do all the engineering work when there's no real outcome. I mean, I can build a model, but what for? And because, based on the question, it might be that you have to get different data. Because different questions have different factors that influence their outcome. If I ask, at which wind speed do we have to stop the lifts because it's too dangerous? I probably need weather data and engineering data of the lifts to make the prediction, but maybe also some sensor data of how their lifts react in real life to wind and weather. Another question, how many skiers eat spaghetti in the skiing area on any given day in the season, can then probably be answered with restaurant sales data and the data of sold tickets. But maybe there are other factors that influence spaghetti consumption on a mountain that we are not aware of. And that's why prediction is always also a bit of an experiment. You can experiment with the data that you have, but you can never be sure if you have missed vital data. That's why you should analyze the data that you have very well. Maybe there are factors that are completely irrelevant that you see as vital for the predictions that will falsify your results. Now, if I have a question that needs to be solved, how do I need to prepare my data set so it is ready to be used in a data mining model? The goal must be to have one single table that contains all the necessary data to train or test the model with. So we need one table where each row is one data point. The granularity must be consistent throughout the table. So either you have the data points per hour, per day, per unit, per year. It must always be the same unit that the data points are measured in. We decided to have the granularity of days since our prediction question was how many skiers per day will be on the mountain. So the granularity was an easy decision for us. The data needs to be well labeled, that you know exactly what is in which column. It needs to be annotated and cleansed. So this means you have to resolve keys that are not self-explaining, and you have to aggregate numbers to the granularity that you need. If you don't have them in this granularity that you that you wish for. So for example, if you have snowfall data per hour and want it per day, you need to aggregate that data to a daily measurement. If I have all the raw data now, the logical next step would be to arrange my data set, as we said. Now let's have a look how the data set needs to be arranged exactly. When building a data set, you should aim for a diversity of data. You should gather both internal and external data when you are a company or a skiing region, for example. The goal is to build a unique data set that will be hard for your competitors to copy. That's why we took the internal historic data that only we had of the skiing region, as well as the weather data, the economic data that was external and public. And that mix was unique. Data mining applications do require a large number of data points, but this doesn't mean that your data set needs a large number of features. The important thing here is we want meaningful data related to the project or related to the questions that we have. You may possess rich, detailed data on a topic that simply isn't very useful. That's why you should reduce your data to the one that you really need. And make some assumptions about the data you require and be careful to record those assumptions. Because if you record them, you can test against them later on to assure that they fulfill your standards. We said before that reducing your data is very important. And this process of reducing data is called feature selection. Every column you want to have in your data set table is called a feature. A random brainstorming of possible features often results in a very large list of attributes. And not all of them are necessarily helpful to build effective classifiers. Selecting only a subset of those initial attributes can be a good idea because it decreases the complexity and also the computing time of the algorithm that you use. And some algorithms are just not very good at dealing with irrelevant or redundant attributes and will deliver, therefore, a lower quality if attribute selection is not performed. So the more noise is in your data, the worse the algorithm perform. For example, it is important that the attributes don't correlate well with each other. They should be really independent. An example of two features that correlated in our dataset were wind speed and air pressure. The wind speed is determined by the rate of air pressure change between two pressure areas. And the greater the pressure difference, the faster the winds. So those attributes would provide us more or less the same information, and we had to choose only one of them. And if we have decided which features are useful and which ones we want in our data set, we end up with a set of final features. Now we have decided of the features that we consider, or we want to consider. What are we going to do if values are missing in our data set? Because data is never complete. So missing values are a very common problem in real-world data. Either there is no data point or it is not complete. Both cases are a problem for many algorithms because they cannot deal with them or misinterpret them. So while building the data set, one has to find a solution on what to do with those missing values. And we have more or less 5 possibilities on how to treat them. The first one is you can delete the row that has missing values and lose the whole data point. You can delete the whole column and remove the features from your data set. That's also possible, but you would lose the feature. You can insert a special dummy value that you later ignore in your analysis. And it's also possible to insert a summary value like the mean or the median for missing values, or for categorical values, the mode. And the 5th possibility is to copy the value from the data object that is most similar in terms of all other attributes and insert this value into the missing value. Number 4 and 5 are very often used because they don't really lose data that you selected. There is also a general consideration on building the data set that you should keep in mind. Larger amounts of training data often outperform more sophisticated modeling methods. This means if you have a large amount of training data, you could choose an algorithm that has a lower accuracy, but a greater speed of learning, instead of using a sample of the data that a highly accurate algorithm can cope with. So if you only have a small amount of data, the accuracy won't be very good, as you can see in the picture here. If you have a lot of data, it improves with every data set that you have. So if you can, always train your model with a very large data set. This is also the reason why you should keep your data in a database while training your model. If you have the performance and the security of the database, you're unlikely to run into problems and into performance issues. So always keep your data inside the database. It's where it belongs. Let's go shortly back to the basics. Let's have a look on the data mining process and what data mining is. Data sources can have very different shapes. They can be other databases, flat files, news feeds, or IoT data that are read. This data is collected and pre-processed and is then stored in a data warehouse. Based on the collection of the data in the data warehouse, datasets can be put together. So important here to say is you should usually take the algorithm to the data and not your data to the algorithm. It makes your life a lot easier. So you create your data set based on the data of the data warehouse. Once you have your data set, you can train your data mining model with your data set. The model can then be used to make predictions or make categorizations or build data clusters, whatever your use case was. Those predictions are additional information to your existing knowledge. This can help you taking the right actions when they are correctly interpreted. So the goal of data mining is to extract information from a data set and transform the information so it can be used further. Data mining is divided in supervised and unsupervised learning. With supervised learning, the algorithm learns on a labeled data set and tries to find a specific solution to a question, as it is done with classification or regression. So like in our example, we have a labeled data set where we know exactly what data is provided to the regression model. With unsupervised learning, the algorithm learns on an unlabeled data set and tries to find pattern in the data on its own. So this is the case with clustering, association analysis, and anomaly detection. Now that we know what data mining is, let's have a look what is inside the data mining model. What do we need to predict something? And inside the model, you have an algorithm. And the algorithm is the thing that calculates your prediction. In the picture, you see a linear regression with two variables, a dependent variable and an independent variable. In a prediction model that uses linear regression, of course, the dependent variable is predicted with one or more independent variables. So through the shape of the data points, a line of regression is calculated that would then be the baseline for the next prediction based on the independent variable. But how are we going to find the right algorithm for our data mining model and the right algorithm for our project? There are different types of data mining functions, and each of them can have multiple possible algorithms to choose from. So which function is the right for our question? and which can be used as a prediction model for skier days, because there are very many of it. We didn't select this very scientifically, and honestly, you really don't have to select this very scientifically, because every data mining function has a name and a short description in the Oracle documentation. So if you read it and have a clear question in mind or a clear task that you want to solve, it should be very clear which data mining functions you have to choose to go further. So let's quickly go through our possibilities. Let's start with anomaly detection. Anomaly detection is listed as an unsupervised data mining function. It is described as a form of classification. It decides if a data point is considered normal or is not. So that's not what we need to get our skier days predicted. But what's about association? The documentation says that association identifies relationships within a data set. That also didn't sound very promising. Let's look at clustering. Clustering defines groups in a data set, but we really don't want to group anything with our skier data, so also not the right one for us. The next one, feature extraction, is for creating an optimized data set that can be used further in a model. So that would be practical to create a data set, but not for predictions. What's about attribute importance? The attribute importance gives us the relative importance of an attribute in predicting an outcome. So that would be very practical when we are doing measurements and optimizing the model. So maybe later, but not for predictions. That leaves us with only two options left. We have classification and we have regression. Both of them can be used for predictions. Classifications are described as models that use historical data to predict a categorical target. And regressions are described as models that use historical data to predict a numerical target. So the only difference is that one predicts a categorical value, like the avalanche risk that can be low, medium, or high, and one predicts a numerical value that is a number. And that's why we decided to go with the regression, because we want the amount of skier as a number. As I said, there are different algorithms for each technique to choose from. With regression, we have the following two possibilities to choose the algorithm. A generalized linear model multiple regression algorithm or a support vector machine algorithm. And here again, you don't need necessarily to study statistics to decide on the algorithm. You could just build two models with the two algorithms and have a look which one gives you the better results. The support vector machine divides the data points into clusters so that they are divided by a clear gap that is as wide as possible, as seen in the left picture. A precondition to use a support vector machine algorithm is a dataset that has a known classification value to make the clustering possible. And multiple linear regression is shown in the right picture. It is used when we want to predict a value of a dependent variable based on the value of two or more variables. And that sounded very promising. And that's why we decided to use the generalized linear model multiple regression for our model. Our dependent variable being amount of skiers, and the independent variables being the data that we have collected before. So the historical data, the weather data, economic data, it's all independent variables. Now that we have known which algorithm to use, how we are going to divide it, the data set that we have, into two data sets. The thing is, you cannot test with the same data you used for training the model. And that's why you need to split them. You still want to use as much data as possible, but also need a certain amount of the data to test the model. For example, an 80% for training and a 20% for testing. One way to do this is Aura hash. Aura hash generates a hash value for a certain expression. This function is used for generating random samples that are reproducible, like when we need a random 10% of the data. In the shown example, 2 sets that are equal in size would be created, so a 50-50% split. To create an 80-20 split of the data set, one would set the maximum amount of buckets to 4, because this starts with 0, so then 5 buckets are filled with values. The second argument you see here is the seed value, or a hash allows to produce different results from the same data set with different seed values. So with the 5 buckets that we have, we use 1 in the first query and 4 of them in the second query. This results in a 20/80 distribution of our data set. That was easy, right? Now let's create the prediction model. Now what we are going to build exactly. We have a short overview over this. We have our training data set that contains most of our data. We need a settings table that tells our model on how to behave if we have special settings that deviate from the default. Out of those 2, we create the prediction model. And to test the prediction model, we have our test data table. This table has the same structure as the training data, but contains different data, and very important, does not contain the target value that has to be predicted. So with the prediction model and test data, we are going to make the prediction. It is then possible to compare the prediction to the actual data. That would be the target value that was removed from the test data set before. And between the prediction and the actual data, the accuracy results and then tells us about how accurate our prediction is. So first we create the settings table that looks like this. This is not really up for discussion, but rather a prerequisite to create a settings table for the model. It defines which settings your model takes, and it also defines which algorithm your model is using. So the settings table looks like this, with a settings name and the settings value that have to be defined. We inserted in our model 3 main things. The first thing was the algorithm that we use, of course. It defined a generalized linear model algorithm that is doing a linear regression over our data points. The second insert enables automatic data preparation. And automatic data preparation is disabled by default. But it is very useful because it transforms the build data according to the requirements of the algorithm. So if it's not perfect yet, it will make perfect. It doesn't change our data table, but the transformation happens when the data, the prediction model is created. The third thing is the definition of how missing values should be treated. So if we still forgot to eliminate some values that are missing in our data set, we define the missing value treatment. We decided to use the mean instead of the missing value. It would also be possible to define that missing values are deleted from the data set, for example. Now let's have a look how this looks on the Oracle Cloud. This is SQL Developer Web, where we create the model settings table that is called model settings with a name and a value. Then we insert the 3 parameters that we talked about, the algorithm name, the auto preparation, and the missing value treatments. Those are then stored in the model settings table. And if we go and check the model settings table, what was inserted, we get those 3 parameters back: the algo name, prep auto, and missing value treatment. So to create the data mining model, we use the DBMS data mining package. You have seen it on the slide before. where the settings were inserted. The create model clause requires us to define a name of our model. It is the object name that will be used further for referencing the model when doing predictions. It's the same as a table name, for example. The data mining functions defines the functions that we use for the model. In our case, this was a regression. Then we need to name the table that contains the training data for the model. The case ID defines the column that labels the granularity. In our case, this was a date column, but it could also be a numerical column with a sequence number. The target column name references the column in our dataset that contains the target value that should be predicted. Since the model needs to learn how to predict the skier number, it needs to know which value should be predicted and which values can be used to calculate the prediction with linear regression. And finally, we reference the settings table that we created before with the parameters. And then the model also knows which settings and which algorithm to choose. But how do I now know which models I already have in my database? Is there a possibility to list them, especially when I have multiple? So you just can make a select from all mining models and get all the models back that you have stored in your database. Great, we have a data mining model and now we want to use it. How are we going to make predictions with this model? So predictions can be done with normal SQL clauses. The prediction functions allows us to reference a model with the model name when doing a selections against a data set that lacks the final target value that should be predicted. And it looks like this. And what we get is a result set, a table with the days and predictions of how many skiers will ski on a certain day. All the numbers that you are going to see here are fake numbers. Unfortunately, I'm not allowed to share the real data with you. But what we can see in the example result set is that on Mondays, we have a pretty low amount of people predicted. And on the weekends, the number increased slightly. Here also the demo how the model is created in SQL Developer Web. We use here the DBMS data mining create model statement. And while creating the models, the database will get some more objects, as you see here on the left side under the tables, that contain specific information about the model. We select here from all mining models and get an overview over the models that we have inside the database. So data mining models are treated the same as other models inside the database. To do the predictions, we then create a select clause with the model that we are using and get a table very similar to the one you saw before inside the presentation, and have a prediction per day of the season. Now let's test our model. What do the numbers say? In the table that you can see our predicted values, we can compare them to the real amount of skiers. And we see that they aren't very accurate. The column delta percentage tells us the accuracy in percentage between the prediction and the real amount of skiers. Although some of the numbers are not bad, like we have a 7% and a 13% variation, there are also cases where we have a 100% deviation between the prediction and the real amount of skiers. You can see them in red. So that needs to change. We cannot have a prediction model that is so inaccurate. So we needed to improve our model. Since my statistical knowledge and the knowledge of my research group partners was a bit limited, we needed help with this one. So we asked around what can we do to improve our model, and had people that came up with suggestions. We ended up with mainly two possibilities. The first one would be feature engineering. That would mean going back to the dataset and restructure and redesign the data in a way that would tell the model which features are more important to get a better prediction. We could also use the attribute importance for this. The second option was to create multiple models, either one model per weekday or a weekday model and a weekend model to eliminate the variety that we had between the single days of the week. So we decided to go with option number 2, with the multiple models, one per weekday and one for the weekends to predict the number of skiers. With one model, we had this set up. We had one training table, one settings table, a model, test data, and one prediction. Now let's have a look how this changed with two models. For the two model approach, we had to split the training data into two sets as well. So in blue, we had the training data for the weekdays, Monday to Friday, and in green, we have the training data for the weekends, for Saturday and Sunday. The settings table remained the same because we want to have the same settings for both models. So while creating the predictions, we use the same settings table. So we create also two prediction models, one for weekdays and one for weekends. We also split the test data into two sets, a weekday set and a weekend set, and then had two predictions that we combined in a SQL clause to still get our one table that I showed before. Let's have a look at the result now. With the two models, we never had a deviation in a delta percentage that was larger than 30%. As you can see here, there are no more red numbers, what means all the percentages are under a 30% mark. The differences in the predictions also improved. When we compare the two prediction sets directly, we see that the numbers improved from the first to the second approach with the two models significantly. Now, of course, you can calculate everything by yourself, but isn't there another way to do this? When you create a model in the database, views are automatically created that provide you with the model statistics. Those views are named like your model, but with a prefix. You can see them under the views listed. To get detailed statistics, for example, per attribute, the $VD view will provide those. And to get the statistics over the whole model and not the single attributes inside the model, the $VG view provides those global statistics. So let's have a look. To get the detailed statistics of the model, we select from the VD view and get coefficient, standard error, p-value, standard coefficient, lower coefficient limit, all those very detailed numbers. And if we select from the VGU, we get general numbers about the model, like the error sum square, dependent mean, all those numbers that you should that you else would have to calculate yourself. So our conclusion as newbies in the data mining environment was that overall it is very easy to learn, but it gets tricky when you have to improve your model and you have no deeper understanding of the algorithm and essential statistics. So it's also essential to know the right people to ask and to understand the domain that you are working in. So if you're fascinated of the topic, the time will fly while implementing your data mining model. And creating the model is easy. The data preparation was the really hard work and took a lot of time. We spent most of our time arranging and rearranging our data set. And the model creation and optimization was a very small part of it, actually. So if you want to improve your skill set, data engineering will be very helpful here. And we were glad that we chose the database as a machine learning platform, because doing data mining where the data is was really efficient, it was reliable, it was very secure, and it was super fast. So if you now want to ask if I'm going to hand out the slides, yeah, sure, I probably will, but they contain a lot of pictures and they're not very helpful. So if you want a written summary of the presentation, you can find a very short one on my Medium page as a blog post. It's, as I said, a lot shorter, but there are the essential points and some scripts there if you want to use them. So do we have any questions in the Q&A that we want to answer?
I have two for you, Jasmin. Thank you, by the way. That was, I really enjoyed that. Nice and clear and concise. You're a very good communicator. So I have two questions. One, Marcelo Proano says, can you elaborate on why you mentioned Oracle Analytics Cloud as not a good tool, unless I heard that wrong? Now,
oh, I didn't say it's not a good tool. It's a very good tool, but it wasn't free for us. It's that tool costs, and we only were allowed to use free tools for doing the data mining. So that wasn't an option. We would love to use it, but it wasn't available for us because we didn't have the budget for tools.
Okay.
But it is a good tool.
Great. Thank you. Then I have another one from Hemant Chitali. How did you do A, identification of the right features, and B, data cleansing? Are there structured methods?
The identification of the features was a very creative process because we just gathered all the data that we could and then looked which features will probably be important based on our own experiences while skiing. Because when you are skiing, you just know when there are a lot of people. That's typically when the weather is very good, when there's not a lot of wind, where there's no fog. So we knew what to look for in the data set. So we took the essential points out of the weather data and also from the economic data, and really looked that it wasn't correlating with each other. So as I said, wind speed and pressure change, we eliminated those to get a feature set that then was up for testing with a model. But what we also did was doing 2 or 3 models with slightly different data sets, and we really got different results. So there's also a part of experimentation when you're doing this.
But there is some real value in subject matter experts being involved.
Yes, yeah. And ask them about the data if you don't know the domain very well. Include the experts. Luckily, we were all skiers, so we knew the domain a bit, but also talking to the people that know this domain very well. And the second point was from the question, that was the data preparation.
It was.
Are there any structured methods?
Structured methods? Yes.
Yeah, we didn't use any structured method to do this, so I'm not sure if there are any. So.
Well, you said you were doing the brainstorming kind of process,
yeah,
first, which is a structured method, right? I think.
Yeah. Okay. Yeah, but it's not really a model or a process that you can go through. Yeah. You just iterate on trying different things and brainstorm on what is important. Yeah.
Yeah. Then Marlon Davis asked, of the weekend skiers, what was the number of skiers that were identified as green to orange?
The difference between the weekends and the weekdays?
It just said of the weekend skiers, what was the number of skiers that were identified as green to orange?
I shortly go back to that overview, just to have. Okay, green to orange, yeah. Green is the first set that we had with the first model that we had, and the orange one is the one with the 2 models. So what you can see here is on the weekends, the number of skiers more than doubles. And that's important to know if you want to have the pists for your own and don't want to share or wait at lifts. On weekends, you can calculate with up to the double or more than double the persons on the slope as on weekdays.
Yeah. Okay. I've got another one here. Abhijit Kulpatkar. Why was the algorithm choice for generalized linear model versus time series forecasting?
Time series forecasting is only the method, the general method that we did. You talk about time series forecasting when you are predicting stuff on a timeline. Like when I'm predicting today what the weather will be tomorrow, and the day after tomorrow, that's a time series forecasting because you have a time series. The other thing is the generalized linear model. That was our algorithm. So those two things don't mix them. It's not the same thing. The algorithm is the way how our model calculated the predictions.
Right.
So it's a matter of what the model does.
Okay, good, thank you. Have you been using OCI free tier for ADB? That's from Antonio Gomez.
Yes, exactly. We used the free tier for all of it, for the data preparation with SQL Developer together. Arranged the table, inserted the data, loaded the data, and created the model on it. So all the scripts that you saw today in the presentations, they work on the free tier.
Okay. Then Teresa Condit just says, can you please post the link to your write-up? Thank you.
Yes, sure. I will post it in the Slack channel and also on my Twitter, so you can have it there.
And then another one from Abhijit. Did you take lagged values of independent variables to forecast the skier's volume for the next week, or was there a different approach?
So I didn't understood the first, what values? Can you repeat that?
Lagged values, L-A-G-G-E-D.
Lagged values.
Like the days before, like how many days, if you're trying to predict Sunday, how many people are on Thursday, Wednesday, Tuesday, that kind of lag.
Okay, we had the weather data 4 days before the actual day. So we could do a 4-day prediction on how many skiers we will have. So we always had that fluent 4-day approach.
Okay. And there was the last question, in fact, and we need to probably get moving, is from Mridul Nath. It could be that the model was using attributes which are not based on time series. Maybe that was the reason for choosing regression. I'm not sure that that's a question, to be honest.
Yeah, we had data that wasn't based on time series, but the data was always related somehow to the date. So like the avalanche risk is usually done for a day, but sometimes also for a week. So those granularity varied, but usually the other data was all date related. So it was a time series.
Yeah, I think people are a little bit misunderstanding some concepts. I think as I understand what Jasmin did here, I thought it was very clever. She used temporal data or lag data, I don't know, or different language translations here, but it's like what was happening in the days leading up to something to then make a prediction for like tomorrow. It's not a time series trying to make a series of predictions over the next 7 days where the lift's going to be. It's using the past observed data, some of it, 2 days ago, 3 days ago, whatever, and the avalanche risk and all those kind of things leading up to, okay, so how many people are going to be in the parking lot and on the lifts tomorrow? Is that a fair statement, Jasmin?
Yes, for the next 4 days. We did that 4-day rolling interval, yeah.
Yeah, it was a prediction rather than a forecast.
Yes, exactly. More a prediction, not a forecast, yeah.
So there's a question here. How do we select the right algorithm in terms of regression approach? There are a few algorithms, test and select. How do you pick like an SVM versus, GLM?
Yeah, just read what the documentation says. And if this fits your problem, you're probably right, because the documentation is very detailed. And if that's not enough, just experiment with it. you can easily do two models and look which one is better.
Yeah. So with that, I think we're going to have to draw that to a close. Jasmin, superb session. Thank you very much for starting us off.
Thank you too.
Excellent. Thank you. Thank you for coming.